Okay, so the initial velocity is 0, right? So this means the initial momentum is 0. This implies that, right? So that means the final momentum, there's no external forces, of course, and this is equal to the final momentum. And here the final momentum will also be 0, and that would equal to the mass of the bullet times the bullet's velocity plus the mass of the rifle times the rifle's velocity. And for this to be 0, and for these two quantities to be non-zero, so the velocity, so these two, the momentum of each object to be non-zero, but the total momentum to be 0, means that these two objects move in the opposite directions, right? According to satisfy this equaling 0. So we have Pi equals P initial, P final, and then we know that this is 0, and then we have R prime, and then I'll go up here, since this is 0, mass VB equals the negative of the rifle, right? And then we solve, it's asking for the VR, like I said earlier. Let me solve. VR is equal to, I'll just move the negative sign over. So we could very easily calculate the velocity of the rifle moving backwards. Extremely easily. So, and we can see that the recoil of the rifle, the velocity of the rifle moving backwards, depends on the ratio of the masses of the bullets compared to the rifle itself. So if you want to reduce this velocity, just increase the size of your rifle and decrease the bullet size, right? So the heavier the rifle is, the less velocity backwards, right? But it's the same recoil momentum, right? So, and if we take it one step further, right? If we have a super heavy gun and we're firing it, right? It will still impart the same momentum to us, right? Because you know, if it's moving backwards into our shoulder, we're going to stop that, right? So there's going to be a change in momentum of the rifle, right? So the force that we feel from that change in momentum of the rifle, we're applying that force to the rifle to change its momentum, and that's what we feel with the kick, with the recoil, right? That's going to stay the same. It's just going to be, it's going to move slower, but there's going to be a lot more mass. So it's going to, we're going to still need to apply the same force to stop it, right? And this becomes very interesting when you start studying the kinetic energy, right? Because now the kinetic energy changes based on V squared. So we'll go more in depth in a few minutes, but let's take a look at this. So the kinetic energy is this. So if we increase the mass of the rifle, right, we're decreasing the velocity proportionally, but what's happening to the kinetic energy of that rifle? So if let's say if we compare two situations, right? Let's look at the kinetic energy, right? We'll have R1, right? We have R1 V1 is equal to R2 V2. We're comparing two situations where the two different rifles, where the mass of one rifle is larger than the mass of the other rifle. Let's write it this way. And this implies that the velocity, for this to be equal, this implies that the velocities, the velocity of R1, of rifle 1, is greater than the velocity of rifle 2. So now let's look at the kinetic energy. Which one has more energy? The energy is not equal between the two. Even though they have the same momentum when they're fired backwards, the kinetic energy won't be the same because it is V squared, right? This V squared takes a different, makes it a different quantity. So the kinetic energy, let's take a look at this. The kinetic energy of R1 is equal to M1 R1, and then I'm going to write, R1, the kinetic energy of R2 is equal to this. Right? Now, if we divide these two quantities, all right, the 2's go away. That should be 2. R1, R1. I wrote out the exponent because if you look, these two quantities are equal to each other. So this cancels out with this, and we're left with R1 over V1. So the ratio of the kinetic energy is not, or the kinetic energies, we should say, are not equal to each other, right? Because we know that the velocities are different. So in the first case where the mass of the rifle is less, the kinetic energy is more. So, and then we'll take the logic by using this. What we'll have, what this shows is that R1 is greater than the kinetic energy of R2, right? So even though the momentum stays the same, the kinetic energy is different, right? What this means is that there's less work done on you, right? With a more massive rifle. Because remember, you're also, when you're slowing it down, you're stopping that rifle using, using your shoulder, the kinetic energy goes to 0, right? So you can figure out the work that the rifle does on you, and it happens to be less, right? So this means that you would have less, that it will push you back less, even though the change in moment, you'll have to apply the same force, it'll do less work on you, right? So really these problems, it's an interplay between the kinetic conservation of the kinetic energies and the conservation of momentum, right? Now we'll come back to the kinetic energy. I just wanted to introduce this weird system where we would have the kinetic energies tell one story. The kinetic energy or the energy tells one story, and the momentum tells another story, right? So now let's look at what happens during a collision. So during a collision, right, let's say, let's take like the tennis racket, right? During the collision, the tennis racket deforms, right? And you can treat this as a spring, as you know, where the force is proportional. You could approximate it as a spring force, right? And then this is dx. So, so the collision, or the time that that the tennis racket interacts with the tennis ball, the force changes, right, over this time. And in the last few problems, we didn't care about the force. We didn't care what happened during the collision. We just cared about before and after. But during the collision, the forces can be quite complicated, right? Now, if we model something like that, and generally this is, if we graph the force, it's generally what the force looks like as a function of time. Is something like this, right? So we start studying the system before the collision, and then the collision happens, the force is applied, and then after the collision, there's no more force. This would be zero. Right? Now, generally, this is what it would look like. This is not a graph. This is not a graph of this, but generally, this is what the force would look like in any collision, not specific to this one, right? And we can see that the force changes, and I'm just showing this one because in this example with the tennis racket, the force changes like an elastic spring. And usually, a lot of these collisions, a lot of these elastic collisions, and we'll go into the definition of elastic collision. A lot of these elastic collisions will obey this law, right? It's an elastic force, and the force will look something like this, right? And what we call this, right? Now this is very different from what we've been dealing with forces, right? We've been dealing with a constant force, right? We apply force and we keep applying that force, right? Every other problem before we've dealt with the force being constant in time. Or, yes. No, we shouldn't say that because with the energy, the force could change. But in the beginning of the semester, when we were really dealing with forces in Newton's second law, the force was pretty much constant throughout the time that we were studying it. Now we have this force, this time-dependent force that only occurs at some finite interval, right? The force only occurs between these 2 points, right? And what we call this, when the force is not constant and occurs over a finite interval, we call this an impulse. We give it an impulse of force, right? Now, let's study this for a minute. So the change in momentum that we study happens across this whole time, right? It's before and after, right? And we can relate it to the force. And then if we bring time to the other side, we see that the change in momentum is equal to the force times that interval that the force is applied. So beforehand, we had this equation. This was the instantaneous change in momentum for the force at that particular instant. Right? This is the instantaneous change in momentum. When we're doing the problem, we were dealing with this, the initial problem of the tennis racket, we considered the force to be almost instantaneous. All the momentum changed within that moment, right? We had in 4 milliseconds. So we multiplied, we took that into account with dt. dt was 4 milliseconds. We just broke this down into one segment, one interval, right? And we just measured the length of that interval. But in general, it's the instantaneous change in momentum. Now, the total change in momentum is given by the force applied over that time, right? And if the force is not constant and depends on time itself, well, we can't just multiply it by the interval, but we have to integrate it, right? We have to do what we did in the past, where we kind of calculate the force at each point and we break it down, and then we add up the forces at each section, right? Like we've done in the past, right? And so that means that we integrate it. We sum up the forces along each infinitesimally small interval. We can calculate the total momentum. So in this case, let's do this. So we go from the initial to the final momentum. All we have to do is integrate. And from the initial time to the final time, and this is equal to the force, right? And this quantity, if we integrate the force over time, this gives us a new quantity, and we call this the impulse. We'll define it by J. J is the impulse, right? So let me write it over here. Right, and this is the impulse. Now, if we take a minute and we look at this, well, what does this look like from the previous section with energy, right? Instead of when we're dealing with energy and work, the integral, we integrated the force with respect to distance, and that gave us the net work. And if we related that to the change in energy, that would equal the change in energy. Here, where we are looking at the force in terms of time, we're integrating it across time, and this would give us the change in momentum, right? So energy is the force applied over a particular distance, right? That's what energy really studies. And here, for the change in momentum is really studying the force applied over time. And that's where energy and momentum separate each other, right? The two different accounting schemes, right? We're accounting for these quantities in two different ways. And even momentum is a bit abstracted. You know, it took me a little bit of time to explain, a little bit of thought to explain exactly what momentum was. And even then, it's this abstract idea of inertia, right? This ability that it wants to stay in motion, right? It needs a force to change its velocity, you know. So even momentum is this abstract accounting terms. And remember, this is a vector quantity, and this will changes things quite a bit. So we'll use conservation of momentum and energy to really fully analyze systems, right? Now, and then the change in momentum is just the area underneath the curve, right? just this area underneath the curve. Take a look at example 9.6 at home. It's pretty simple. It's a pretty simple one, but I want to move on. Okay. Now let's consider energy and momentum in collisions, right? And when we consider both energy and momentum, we could break these collisions down into different categories, right? And we'll break it down into elastic, what's known as elastic collisions, and inelastic collisions, right? So we'll define elastic collisions as when both the momentum or the change in momentum is 0 and the change in kinetic energy is also 0. So that means that both are conserved. Right? So in this case, both are conserved. And this usually happens when in that initial situation where we have the two balls colliding, right? And they bounce back. They collide, and then they go back. And then they repel, well, they change their velocity to move away from each other. That's usually an elastic collision. Then we have an inelastic collision. And in this case, we have the momentum conserved, the change, and the kinetic energy changes. The change in kinetic energy is not 0. And the way we account for it, let's say if we have these two balls, let's consider this situation. Let's say now this situation is inelastic, that during this collision, there's some loss of energy. They're not perfect. They're not a perfect spring. The forces aren't. The energy is not conserved. It's not a perfect conservative force. Some of it is lost into heat. In this case, we would have the kinetic energy. I'm going to use K for kinetic energy instead of KE for now. Here, we'll have this situation. And this is equal to the kinetic energy after the collision plus whatever energy is lost in the system, thermal and other forms of energy. Right? Oh, somebody hitting a baseball, right? that's an inelastic collision, right? And you can hear the sound of the ball hitting the bat, right? And part of that energy is transferred into sound. So you would have this case, right? So these are two different cases, right? And what we say is that when it's an elastic collision, we say that it's perfectly, okay. So we have an elastic collision and then we have inelastic collisions. An elastic collision is easy to deal with because both are conserved. And an inelastic collision, the amount that's not conserved can change. And we get this, so we get different levels of inelastic collisions. And in particular, the maximum energy loss, so we can't lose all our energy. Well, we can in certain systems, but remember that we always have to satisfy the change in momentum. So how much energy we lose is really constrained about satisfying the change in momentum. And when we maximize the loss of when we maximize this change in energy while satisfying this is called a perfectly inelastic collision. So a perfectly inelastic collision is when the change in momentum is the greatest. So when does this happen? We actually did two examples when this occurs. So let me erase this now. This occurs when the objects join each other, actually, and it's easier to think of the rifle. Right, we have the bullet. What's the initial kinetic energy of the system? It's 0, right? And then after, it has some finite value, right? VR so in this system, so in this system, we maximize the change in kinetic energy, right? It goes from 0 to whatever velocities that is traveling at, right? The other system is what the train cars, when they combine. This is also perfectly inelastic. And this is a little bit harder to see, but if you think about it, this is because of this velocity term. And here the KE before initial KE. If you look at it, we're really, when it combines like this, we're really giving it, we're transferring a lot of the momentum to the mass. Remember how it was, the new velocity was proportional to the two masses. And it's this square term that really tells you that this is that the change in momentum is maximized. So these two scenarios are perfectly inelastic collisions. All right, let's move on to some examples. When we run out of time here in 10 minutes, we'll take a 5-minute break and then we'll come back and finish. Okay. So now, if we have a perfectly inelastic collision, we have another equation to use to determine the velocities. So for an elastic collision, right, we have two equations. So let's say if we have two balls, and then this is before, let's say this is moving faster, so it catches up, and then after, it'll look something like this, right? So let's see how these collisions look like, head-on collision. So we have this equation, right? And then this is equal to MA plus A after, right? And then we have this equation. All right. We have these two equations. All right. So let's relate the velocities. So now what I'll do is I'll group the M terms. So we have MA VA minus VA prime after a collision. Right? And we have this. And then we'll do the same thing for this. All the 2's go away because it's a coefficient for every term. And we'll have MA VA squared minus VA prime squared VB minus VB. We'll have this. Now, we'll use a little identity algebraic identity. If you remember from algebra, VA squared minus VA squared minus another term, in this case, VA prime squared, this is equal to, we could factor this, right? When we factor it, we discover that it's really this multiplied by this, right? When we just factor it, we're just factoring it. But it turns out to be this, and this is equal to this. Okay? We have this over here. Now, let me go back up to the top. I'll erase stuff. Now we go back up to the top. Let's continue. Now let's divide this by the momentum. Remember, this is P, and this is E. So let's divide P divided by E. Right? So we'll divide it. And what happens is that if we divide each term by each other, this cancels out with, these two terms cancel out. Oh, I'm sorry. I meant E divided by P. We do E divided by P. Right? And we discover that this term cancels out with this term, and we're left with this. Right? Isn't that interesting that the initial and final velocities don't depend on the mass anymore? Right? It's kind of cool. And it comes from the fact that we conserve energy. We have that constraint. And let's do this a little bit differently. So the difference, we'll look at it a little bit differently. The difference in the two velocities will equal the difference in the two velocities at the end. I'll write this a little bit differently. So the difference in the two velocities is equal to the negative of the difference in the two velocities. What does this mean? So if we have something in this situation where VA is larger than VB, after the collision, VA is going to become smaller than VB, right? Now, what about in a head-on collision when they come together? This still satisfies that equation. We initially studied where the masses are equal, but when we study where the masses aren't equal, they will bounce off of each other and go in the opposite directions, right? And that's